In this class, we will discuss a problem on biaxial bending of a beam column. So, it is an examination problem, VTU July 2022. The data is given like this. The effective length of the beam column is 3.4 meters about both the axes, that means about both Y and Z axis. Section provided is ISHB 300 at 588 Newton per meter. So, already section is provided. So, we have to check the adequacy of that section. Factored axial load on the beam column is 500 kN. Factored moments are in both the directions. That is why it is called as biaxial bending case. So, you can see in this figure, so the axial load will be acting like this at this junction. So, this is the column. So, if you take MZ and MY, so two moments will be there. So, you will be having moments in two directions. Normally, this is the case in the case of a space frame structure. So, it will be subjected to two moments and one axial force. So, here both the moments are significant, of course. If one moment is very less compared to the other one, then we can almost can treat it as a uniaxial bending. But in this problem, of course, even though the moments are less in the MY moments are less, one is negative, another is positive. At the bottom it is negative and the top it is positive. Whereas MZ is both positive at both the top and bottom, they are the end moments. So, moment will be here, moment will be here, of course, axial load will be here. So, these are the moments in kilonewton meters that is given, and of course, grade of steel is Fy 250 and Young's modulus 2 into 10 power 5 Newton per meter square. The question is, check the adequacy of this section. So, in the last lecture, I have explained about uniaxial bending, where the values of axial load and only one moment were given, P and MZ were given. Here P, My, MZ, all three are given. So, anyway, I have explained about the different checks we have to carry out to check the adequacy of the section. There are four different checks which is given in the IS code. So, if all the four checks are satisfied, then definitely we can say that this section can take care of both the axial load and the moments. Now, in the first step, let us write down the properties of the given ISHB 300. So, these are the properties which you can obtain from steel tables. So, the geometrical properties are like this. This is the Z axis, this is the Y axis, this is capital H. Overall depth is capital H. D is the depth of web. TF is thickness of flange, TW is thickness of web, R1 is radius at root, and AE is nothing but AG. Gross cross-sectional area and the effective cross-sectional area, they are same in this case. So, these are the values. So, you can note down from the steel tables, and we need the values of this section modulus also, both elastic section modulus as well as plastic section modulus. So, ZEZ is the elastic section modulus about Z axis, which is this value. ZEY is the elastic section modulus about the Y axis. So, normally this is less than this. ZPZ is the plastic section modulus about Z axis, and IZ and IY are the moments of inertia of this section about Z and Y axis. All these details you can get from the steel tables. And now for the analysis or for checking the section, normally we take the higher value of the moments. So, here among these two, the higher value is 15. So, I am going to take maximum MZ as 15, because if it is satisfied for 15, then automatically it will satisfy for 7. And for My maximum negative value, of course, 1. So, I am going to take it as minus 1 kilonewton meter as the maximum My value. Anyway, we are interested only in the magnitude value. We are not worried about direction. And this value of axial load, factored axial load is given as 500 kN. All these are factored loads and moments. So, here he has given the factored load as 500 kN, which is nothing but N in the code. Now, we will start one by one whether the section satisfies all the four checks. The first important check is check for local capacity of the section. The equation is available in page number 71 of the code IS 800. So this is the equation that should be satisfied for biaxial bending. N by Nd plus My by Mdy plus Mz plus Mdz should be less than or equal to 1. This is for a semi-compact section. Please note that this is for a semi-compact section. So before using this, we can check the section for IS 300 whether it is a semi-compact or plastic or compact section. So for that, we have to take these two ratios, B by Tf and D by Tw. So all this I have explained in the earlier lectures. So B is half of Bf. So if you take the ratio, you are getting 11.79, which is less than 15.7 epsilon. Epsilon is 1 here because epsilon is 250 divided by Fy and the root. Here Fy is 250 itself, therefore it becomes 1. So it is a semi-compact section. So this you can refer table 2, which is there in page 18 of the code. So you know how to classify the sections. So since that value is less than 15.7, so of course it becomes a semi-compact section. Flange is a semi-compact. Now coming to the web portion, it is d by Tw, where d is the depth of the web, Tw is thickness of web. If you take Z ratio, it is 27.3, which is less than 84 epsilon, that is 84, which becomes plastic. Please note that here web is plastic, whereas flange is semi-compact. So in that case, I have told you that you have to go for the lower strength section, that is you have to keep it as semi-compact. So this is very important. If it is semi-compact, then this is the equation, this is the expression that should be satisfied for local capacity of the section. If it becomes plastic or compact, there is another section, there is another formula which is there in page 70 of the code. 70 for plastic and compact sections, you can see that My by Mndy whole to the power of alpha 1 plus Mz by Mndz whole to the power of alpha 2 should be less than or equal to 1. So that is the equation you can use for if the section is plastic or compact section. Now since it is semi-compact, we have to use this equation. So considerable, that is you can use this equation considerably. Now we have to substitute all these 6 values. 6 values you have to substitute, and we have to check that the sum of these 3 ratios should be less than or equal to 1. It should never exceed 1. So here now let us calculate one by one. So the first value I need Nd value. So Nd is nothing but it is the design compressive strength due to yielding, which is given by this formula Ag into Fy by gamma Mo. So Ag is gross cross-section area 8025 mm square, Fy is 250 Newton per mm square, gamma Mo is 1.1 partial safety factor. If you simplify that, you will get 1823.86 kilonewton. So you are going to get a Newton, that you can convert to kilonewton. That is the value of Nd. Then we need this value of Mdz and Mdy. So for that the formula is this. Mdz is beta b into Zpz into Fy by gamma Mo. Everything is available in the code. Since it is a semi-compact section, beta b becomes Zdz by Zpz. Please note, beta b is this. Whereas if it is plastic or compact section, you have to take beta b as 1. So into Zpz into Fy by gamma Mo, this Zpz will get cancelled. So you will be left with Zdz into Fy by gamma Mo. So you can see here Zdz is 863.3 to 10 power 3 for the given section into 250 by 1.1. You are going to get a Newton millimeter. If you convert it to kilonewton meter, it becomes 196.2 kilonewton meter. Next we need Mdy. Similar to this, we can take the value of Mdy as instead of Zdz, you have to take Zy. So 178.4 to 10 power 3 into 250 by 1.1, which comes out to be 40.545 kilonewton meter. Now substitute all the values in this equation 1 for the first check. N is 500, it is given in the problem. 500 divided by 1823.86 is Nd plus My, higher value I am taking minus 1. Of course, anyway, I have to consider the magnitude only. Forget about the that is sign. So 1 is the value divided by Mdy is 40.545 plus mz is higher value is 15. So 15 divided by 196.2 is the value of mdz. If you take the sum of these three ratios, it is coming 0.375, which is definitely less than 1. Therefore, the first check is satisfied. So because it should be less than 1, the first check is satisfied. Now coming to the second check. So we have to see the second check now. So we have to check all the four criteria which is given in the code for checking the adequacy of the given section. Of course, this is an analysis type of problem. In a design problem, what they will give is only loads will be given. You will not be given the section. So we have to assume suitable section. Then we have to check once again four criteria. That is in the design problem. So in analysis problem, so section will be given, and you have to check whether the criteria is satisfied as per the codal provision. Now the second one is check for member buckling resistance in compression. These are the wordings. Check for member buckling strength in compression. Buckling strength in compression. See, this one I have told you in the last lecture, also the last problem also. When you are analyzing a beam column or designing a beam column, it behaves both as a column and a beam. So normally column will take compressive load and beam will take the bending moment. So now we are treating that it is a column. So compression means it is a column. The check here is what we have to do is whatever design compressive strength will be there. We can call them as PDY and PDZ. This should be greater than or equal to P. So that is 500. So this is the check we have to carry out to check the section for compression. Okay. So whether that section can take up sufficient compression or not. So that means we need to calculate these two values. So that in another way, that whatever beam column is given, that is treated as a column and it is checked for compression. Now for that of course here he has given effective length, he has given KLY both and KLZ. Both will be 3.4 meter or 3400 mm. The effective length in either direction he has given this value. Now we need the value of RY and RZ for this radius of gyration of the ISHB 300 about Y and Z axis. From the steel tables you can get RY value is 52.9 mm and RZ value is 127 mm. So these two are the radius of gyration along the Y and Z axis of that particular section. Now if you take this ratio KLY by RY, effective length divided by radius of gyration, that is your slenderness ratio along Y direction, which comes out to be here 3400 divided by 52.9, which is 64.2. Similarly, if you take KLZ by RZ, it is 3400 divided by 127. So he has given same length along both the directions. Therefore, we have to take KLY is equal to KLZ. So this value comes out to be 26.8. Now once you get these two values, so from the table which is available in the code, so you can refer that table for compression. The table number, of course in the last problem also I had explained it. So the table number and the buckling class number, so they are given in page 44. See, they are given in page 44. So for that, to check that, what we have to do here is, so we have to take the ratio of, so you just refer the table number 10 given in page 44. Table 10 given in page 44. This gives an idea about in which way that buckling takes place. So buckling has been classified into 4 types, A, B, C, D, like that. So in which category this section will fail? So for that I need to calculate a ratio called H by VF. You can refer the table for that. H here is overall depth of the given section 300 mm divided by VF is 250, which comes out to be 1.2. There is a criteria there, so it is greater than or equal to 1.2. Therefore, it is equal to 1.2. Then TF value, thickness of flange, of course in this case it is 10.6 mm. So here you can take it as less than 100. So for this category, if you refer that rolled I section from table 10, page 44 of the code, so for this category, about, you can see here, it comes under the first one itself. So TF is second one. So second one, H by BF is less than or equal to 1.2. TF is less than or equal to 100 mm. So you can see the second row. It buckles. Buckling about z-axis will be class B and buckling about y-axis will be class C. So please note down that. So from the table, what you can write here is, so buckling about z-axis. So the buckling class is B. Buckling class is B. But suppose if it buckles about y-axis, so the buckling class is C. So these two you have to note down. Now based on this, you have to refer the particular table which is given in the previous pages. So suppose if you take buckling about z-axis, this one, then you go to table 9b. Table 9b, which is there in page 41 of the code. Page 41 of the code. So what you will get there is, for the value of KL by R, it is given in the left side column, and for a given value of Fy, of course Fy here is 250 MPa, you can directly read the value of FCD. FCD, that is the design bending compressive stress. So the design bending compressive stress you can read. Of course this is in about z-axis. Similarly, for the second one, about y-axis, buckling class is C, So buckling class C means you have to go to page 42. Page 42 of the code. So refer table 9C, page 42 of the code, and get the value of another FCD but above y-axis. So these two values we need. Of course you have to interpolate the values. You may not directly get the reading. So because your KL by R value may not be exactly whatever is given in the table there. So from if interpolation is done, you can get the value of FCD for the first case. You are going to get FCD as 215. Approximately it is 215 Newton per mm square. That is about the z-axis. Then about the y-axis, for the second case you will get 162. So all this you can check. 162. So these are the design bending stress values, bending compressive stress values. Now once you get these values, if you want PDY, so this PDY is given by FCDY into this area, cross sectional area of the section. So this is stress multiplied by the area gives the force, that is the design compressive strength in along y direction. You are going to get the value as 162 into 8025 is the area. You will get the value in Newton. So Newton will be 1300 into 10 power 3, or you can write as 1300 kilonewton. So this is the value of PDY. Then PDZ of course will be slightly more than this because FCDZ will be more than FCDY into AE. AE remains same. So here it is 215 into 8025, which comes out to be 1725.4 into 10 power 3 Newton, which is 1725.4 kilonewton. So these two are the values of PDY and PDZ. So you can observe here both these two are greater than P. You can see here. So this is also greater than 500. This is also greater than 500. Therefore, the strength is more than the axial load. So therefore, you can say that it is safe against compression. So that means that beam column, whatever is given, it is safe if it is treated independently as a column. So this is the second check we have to carry out. Now the third check. So third check is check for member buckling resistance in bending. So this is for compression. Check for compression. Third check is check for bending. Compression check is over. Now we have to check whether the beam column is safe tilting it as a beam. So both the effects we are considering separately. Compression effect and bending effect we are considering separately, and then we have last check is the combined effect of both compression and bending. Now the third check is check for member buckling resistance in bending. Third one. Check for member buckling resistance in bending, treating the beam column as a beam alone, whether it is satisfied. So for that, of course, we have to use the procedure which is given in the code in page 54 of the code. So treating that as an unrestrained beam. So we have how to design the unrestrained beam. So using that, of course, we need to calculate one important elastic buckling torsional moment, MCR, which is given by C1 into root of pi square EIY by L square LT into GIT plus pi square EIW divided by L square LT. So these equations, this moment we have to calculate after substituting all these values here. Of course, this LLT we have to take 3400 mm effective length of the column. GIT you know how to compute for the given I section, which is summation BI PI cube by 3, 2 flanges and 1 web, and IW you know how to compute. This is the torsion constant IT, this is the warping constant, 1 minus beta f into beta f into IY into HY square. So all the values, of course beta f value is 0.5 here, because it is a symmetrical section, you can take beta f as 0.5. This equation is available in page 129 of the code. So all these things I have explained in the earlier lectures. So E value of course 2 into 10 power 5 Newton per mm square, G value for steel 76.9 into 10 power 3. All those values, if you substitute and simplify, you will get the value of MCR. I want you to work out this, because already I have explained in the earlier examples. So many examples I have explained this how to compute. Then after this, you need to compute the value of certain parameters we need to compute. So here the parameters which you have to compute are that C1 value, of course you need to get. C1 value you need to get here. That C1 value, of course, it depends on this psi value, which is nothing but the ratio of M Z at the top to the MZ at the bottom, or whichever lower value is there, that should be there in the top, higher value should be there in the bottom. So here you can see it is 7 by 15. So here the higher value is at the bottom, higher value is at the top, lower value is at the bottom. So you can take this as MZ2 by MZ1, something like this. So based on this value of psi, you can get the value of C1. Of course, these things I have explained in the procedure. So the C1 value you can get from page number 72 in the code. 72 in the code, you can refer that. So you can get the value of C1. So anyway, this beam column example, it is from the pages 70, 71 and 72 of the code. So once you get this C1 value, then substitute all the values here, get the value of MCR. So once you get MCR, then the other parameters which you need to find are these things, that is lambda LT you have to compute. So you know how to calculate the parameters. All the expressions are given in page 54 only. So you have to get the value of lambda LT. So this lambda LT, non-dimensional slenderness ratio, which is given by beta of B into ZPZ into Fy by MCR under root. So this is a dimensionless number. Then after that we need to calculate phi LT, which is 0.5 into 1 plus alpha LT into lambda LT minus 0.2 plus lambda LT square. This is the value. Then of course if this lambda LT is greater than 0.4, then you need to consider the effect of torsional buckling. Here of course in this problem you are going to get that. Then you have to calculate xi LT. Xi LT is 1 divided by phi LT plus phi square LT minus lambda square LT equal to the power of 0.5. You are going to get another number here. Then you need to calculate the design bending compressive stress FBD. So this FBD is equal to xi LT into Fy by gamma MO. So this value will be getting in Newton per mm square. Then after this we have to calculate the design bending strength, which is MdZ, which is nothing but beta of B into ZpZ into FBD. In newtons you are going to get, then you can convert it to Newton millimeter you are going to get, you can convert it into kilonewton meter. The check is this should be greater than your mz max. Of course, here you are going to get, you can check that mz max here is 15, so you are going to get more than 15. So this step I want you to complete. This is the check. Then the last check is very important. That is for the combined effect of both compression and bending. Once again you go back to page number 71 of the code. 71 of the code has given two equations we have to take now, because it is a biaxial bending. So check number 4 is for the combined effect of both compression and bending. So we can call that check as check for overall member buckling. So fourth check is check for overall member buckling resistance for combined buckling resistance for combined bending and axial compression. See, here we have to consider both the effects of bending as well as axial compression. So we have to refer page 71. There are two equations for biaxial bending. So you have to refer both. If it is uniaxial, only one equation, which I have done in the last problem. So here we have to use two equations. The first equation is, I am going to write this equations. So we have to calculate all those parameters which are required. P by Pdy plus Ky into Cmy into My by Mdy plus KLT into mz by mdz should be less than or equal to 1. This is the first equation. The second equation is P by PdZ plus 0.6 times Ky. You need not remember anything. Everything is given in the code. Cmy into my by mdy plus Kz into Cmz into mz divided by mdz. This also should be less than or equal to 1. So these two, A and B, I call them. So these two should be, equations should be satisfied. Then only we say that the combined effect of compression and bending has taken care by the given section. Now we will see what are the values you know here among these, what are the values you know and what are the values you need to find out. So all the explanations are given in the code. CMY and CMZ, they are called as equivalent uniform moment factors as per the table 18. So which is given in page number, next page, in page number 72. So these values CMY and CMZ, so these values, these two values are given in table 18 of page 72 of the code. Next page it is there. Then P is the applied axial compression under factor load, which is 500 kilonewton. So P is given as 500 kilonewton. It is given in the problem. That value you take. Then PDY and PDZ already we have calculated. In one of the checks we have calculated that. So the value of PDY is 1300 kilonewton. And this value is 1725.4 kilonewton. So it is already calculated in the earlier steps. These two are calculated. Then we need to find the MZ, MY and MDY also, they are known. So what are the known things I will write down? My and MDY, similarly MZ and MDZ. So these four moment values we know. So the value of My is the higher value, that is -1, of course, kilonewton meter. Of course, numerical value we take in the formula +1 kilonewton meter. Then we have this MDY value, already we have calculated in the earlier step. MDY has come to 40.545 kilonewton meter, and MZ is the higher of those two, which is 15 kilonewton meter, and MDZ also we have calculated earlier. So this is calculated in the earlier steps. MDZ value we got 196.2 kilonewton meter. This is also calculated earlier. So these are the so we know now this value, this value. This is over, this is over, this is over, this is over. Here this is over, this is known. Then MDY, MY, MZ, MDZ. Now the unknowns are KY, CMY, KLT, and here KY, KZ, CMY, CMZ. So these are the unknown values. So let us see how we can compute those values. Of course, for finding this KY and KZ, they have given equations in the same page, that is page 71. They have given the equation. See here, KY is equal to, I write now, so let us calculate them one by one. KY is equal to 1 plus lambda y minus 0.2 into ny, which should be, of course, should be less than or equal to 1 plus 0.8 into ny. So this is a check for that. Now let us see how we can compute this. Here ny and nz. So ny is nothing but what he says here is it is the ratio of actual applied axial force to the design axial strength for buckling about the y and z axis respectively. So that means here ny is equal to what we can write here is there is nothing but P divided by P dy. Whatever action is acting and whatever strength it is having. So P divided by P dy, I think that is 500 divided by 1300. You are going to get the value as 0.38. Similarly, Nz is P divided by PdZ. PdZ. So it is nothing but now 500 divided by 1725.4 PdZ. So this value is slightly less, which you are going to get it as 0.29. 0.29. So this is about y-axis and z-axis. Now I need to calculate the value of lambda y. So lambda y is nothing but, so the formula to calculate lambda y is root of fy by FCRY. FCRY. Whereas, what is that FCRY? So all these equations are available in the page which is given in 54 also. The same expressions are available. So this FCRY is given by pi square E divided by, see here how we have to calculate that, KLY by RY whole square. That is Taylor's ratio about the y-axis square of that. So if you substitute all these values, so here E is 2 into 10 power 5, KLY is 3400, RY of course I have given there some 59.2 something. If you substitute those values, this FCRY crippling stress value along y direction 478.9. 478.9 Newton per mm square. So all these values you please check the values. So any correction is there, you can make yourself. So 478.9 Newton per mm square. So therefore your lambda y now becomes this is 250 divided by 478.9 under root. So this value, lambda y value, you are getting 0.72. Now once you get lambda y value, you substitute here in this equation. If you substitute in this equation and get the value of ky. So if you substitute those values, so your ky value becomes now 1 plus 0.72 minus 0.2 into ny is 0.38. So just simplify that. You will be getting 1.2 and check that whether that is less than or equal to 1 plus 0.8 ny. So that is, it should be less than or equal to 1 plus 0.8 into ny is once again 0.38. So if you simplify this, you get 1.304. So definitely this 1.2 is less than 1 is less than 1.304. Therefore, ky value you can take 1.2. So this ky value we got now. So this ky value is 1.2. Here also this ky value is 1.2. Okay. So now we got the value of ky. Next we need to calculate this KLT, CMY and CMZ. So those three values we require. So for that what we will do here is this KLT value and also we need the value of KZ. Now similar to KY, we will calculate this KZ value. So same in the same page he has given another expression KZ. For calculating KZ, the formula is 1 plus lambda z minus 0.2 into nz. And on the similar lines, this should be, he has given there, it should be less than or equal to 1 plus 0.8 into 1 plus 0.8 into nz. Is a check. Yes, now just how we calculated lambda y here, same procedure is used to calculate lambda z. So lambda z here is Fy by FCR z. Instead of y, we have to take z under root. So what is this FCR? FCR z. FCR z here is similar to that pi square E divided by KLZ by RZ square. So here we are taking the tenderness ratio along the z direction. So you know the values. Here only difference is RZ. RZ for that ISHB 300 section is 127 mm. So substitute those values and simplify. You will get FCR Z value. The FCR Z value 2748.3. So we are going to get a higher value here. This is the value of FCR Z. Now substitute that value here. 250 divided by 2748.3 under root. So if you simplify that, lambda z, lambda z value, you are getting 0.3. That value you substitute back here in this. Substitute back in that. So you get therefore kz is equal to 1 plus lambda z is 0.3 minus 0.2 into nz is this 0.29. 0.29. So if you simplify this, you will be getting 1.029. 1.029. Definitely this is less than this 1 plus 0.8 into 0.29. So you can check that. So then that means this is the value of lambda z. You can that is kz you can take. So kz value is also known now. This value is 1.029. Now we got ky value 1.2, kz value 1.029. So now klt. So usually this klt will be normally it will be equal to that for that also he has given formula there. So you can just take the formula. Before that we will take up this one. I want to have the value of CMY and CMZ. See these two values. Modification factor values I need. So now let me calculate those values CMY and CMZ. Now for that we have to refer whatever table 18 is there in page number 72, that we have to use. So if you refer the table, you can say in the third column it is given. Of course it depends on the value of psi. So here please note that psi is nothing but the ratio of the moments at the top and the bottom. So we have to take the higher value at the bottom, lower value at the top. Now if I take psi y is the ratio of the moments along y direction, which is negative here, minus 0.75 divided by 1, which is minus 0.75. This is along y direction, the value of psi. Along z direction, the value of psi is 7 divided by 15, which is positive. So which you can take it as psi z value is 0.75, 7 divided by 15, I will tell you the value. So it comes out to be 7 divided by 15, of course 0.45 something you may get. Okay, so that is the value. Now once you have these two values, you see the range of psi value in the table 18. In table 18, page of course 72, you can see CMY and CMZ values. So for you can see for concentrated load we have to take. So for concentrated load, because axial load is a concentrated load, 0.4 plus 0.6 plus 0.4 psi, it should be greater than or equal to 0.4. So this is the condition under concentrated load as well as uniform loading. So the values of CMY I can take now 0.6 plus 0.4 into psi y I have to do this value. So which comes out to be 0.6 plus 0.4 into minus 0.75. Of course, if you simplify that, you will be getting CMY value as 0.3. So it should be greater than or equal to 0.4 means the higher value you have to take 0.4. Therefore, higher value should be taken. So this is actually less than 0.4. Therefore, restrict take CMY is equal to 0.4. Next, coming to CMZ. CMZ is same thing 0.6 plus 0.4 psi z. So it is 0.6 plus 0.4 into that is 7 by 15. So whatever you take 7 by 15. So that will be maybe slightly 7 by 15 I will write. So this value will be 0.79. So definitely this is greater than 0.4. So the thing is, if it is less than 0.4, restrict it to 0.4. If it is greater than 0.4, whatever value you get, that you will take. So CMY is this, CMZ is this. So now these two we got now. CMY we got, CMZ also we got. Now the last value we need is this value, KLT value. So for finding KLT, we have we have the expression in the same page 71. So KLT is equal to 1 minus 0.1 lambda LT into NY divided by CMLT minus 0.25. Of course, there is a check for this. The check is it should be greater than or equal to 1 minus 0.1 NY divided by CMLT minus 0.25. So this is the check. Okay. So here the thing is CMLT can be taken as equal to CMZ normally. That is the higher value which you can take 0.79. So CMLT can be taken as 0.79. Lambda LT value already we have got that lambda LT value as 0.476. 0.476 is the lambda LT value. Then we need what else we need? So lambda LT is 0.476. This value, NY value, of course, we have found out that in the last step. I think is 0.38, and this value is 0.79. If you substitute all these values and simplify, you will get KLT as 0.967. KLT is equal to 0.967. Now this value is also obtained, KLT. Now we have all these values now. So P, PDY, KY, CMY, CMZ, MY, MDY, MZ, MDZ, then KZ, KLT. So all these values we know now. Now what the next step is, you substitute the respective values in both the equations A and B. So this is B. So in both the equations A and B, and check whether you are going to get the sum of the ratios as less than 1. Of course, I have done it here. Final values I am going to give after substituting the values in equations A and B, expressions A and B, and simplifying. So you are going to get these values. You please check that. So substituting all values in A and B. So in the first equation, if you substitute in A, so LHS, what you are going to get is, I will tell you that LHS becomes 0.478. 0.478, which is definitely less than 1, so satisfied. So along one equation satisfied. Second equation B, LHS, if you substitute all the values and simplify, you are going to get 0.366, which is also less than 1. So it is also satisfied. So the fourth check is also satisfied for biaxial bending for the overall member, both along y and z direction as well as the axial direction. So here we can see the first term represents the ratio along the axial direction, second term along the y direction moment, third term along the z direction moment. Similarly, here also we have since we have moment along both the directions, so for biaxial case you will be having two equations, whereas for the uniaxial case you have only one equation, which I have explained in the earlier lecture. So this is how we have to check the adequacy of the given section when the beam column is subjected to all the three, that is axial load, axial compressive load, moment along y direction, moment along z direction. If uniform moment is there at top and bottom, then psi value will be equal to 1. Please remember that psi value is the ratio of the moments at top and bottom, that is young moments, higher value at the denominator, lower value of the numerator. If both the moments are uniform moments, then we have to take the value of psi as 1. So this is how we have to do. Of course, it's a very lengthy process. In the examination, of course, this is an examination problem given for 20 marks. I don't know if you practice it properly. Minimum, I think you require 40 to 45 minutes to analyze this. Okay, because you have to carry out 4 different checks. If they ask you in the examination a particular check, then you can do that particular check only. But for that also, we require certain values, because this PDY, PDZ values you can get from the check for compression. This MDY, MDZ values you can get the values from the check for bending. And of course, the third one is that MCR value we have to compute. Then you have to calculate MDZ value, and this is the fourth check. So if you do all the 4 checks, then that is the complete design of a beam column.